Hello students, good afternoon. Hope you are doing well. Today's topic, AC circuits. This chapter contributes 1 to 3 questions in NEET exam. Last May 3rd exam, 2 questions are given. Usually 1 to 3 questions it contributes to NEET exam. And in this chapter, you need to focus on concepts, formulae and numerical problems. Concepts, formulae and numerical problems you need to focus. In this concepts also important. I want to means phase difference values, phase difference in various circuits, phase difference between current and EMF, and resonance conditions of LCR circuit. Different concepts also important in this. So first I want to revise you just briefly some important concepts in this. First thing is you need to this chapter RMS values of current and EMF, they are important in this. RMS current, RMS EMF relations. RMS EMF, RMS current. RMS current is peak value of current, maximum current by root 2. ERMS is peak value of EMF, maximum EMF by root 2. Average current, average EMF also there now for half cycle, average EMF 2I naught by average current 2I naught by pi, average EMF 2E naught by pi, so on. These relations you need to revise. Next, I will give you one table here. One table I will give you now. Circuit, resistance or reactance, whatever you call, or impedance, this of that particular circuit, and then phase difference. I am writing here phase difference between current and EMF of the source. Between current and EMF of the source. Voltage of source. Between them, I am writing phase difference. Then power factor. And last, power. Average power. This table, remember, first one is pure resistor circuit. AC circuit with pure resistor. Resistance or phase difference 0. Power factor 1. Power factor means cos phi value. That is R by Z. Power factor is 1. Power is ERMS into IRMS. ERMS into IRMS, which is also equal to ERMS E naught by root 2, IRMS I naught by root 2. So you'll get E naught I naught by 2. This is for pure resistor circuit. And then pure inductor. Pure inductor circuit, inductive reactance L omega. Phase difference pi by 2. Pi by 2. Who will lead current? EMF. Who will lead? Who will lag? I am writing with respect to current. In pure inductor circuit, current lags EMF by pi by 2 phase difference. Power factor 0. Average power 0. This is pure inductor. Then pure capacitor. Capacitive reactance 1 by C omega ohms. capacitive reactance, where omega is the angular frequency of the source. And phase difference between current and EMF of the source, here also pi by 2. Here in capacitor, pure capacitor circuit, current leads the EMF by phase angle, power factor 0, and average power 0. Resistor, pure inductor circuit, AC circuit, pure capacitor, AC circuit. Okay. You need to remember these points. Questions will be on these points only. This impedance, phase difference, power factor. On this only questions will be there usually. Okay, now I'm cleaning this, and here I'm writing the other three. Other three circuits, LR, CR, LCR. LR, CR, LCR. LR series AC circuit. In this impedance, the resultant resistance impedance under root R square plus XL square, that is under root R square plus L omega whole square. That is the impedance. And phase difference. In this LR circuit, phase difference between current and EMF lies between 0 and pi by 2. So I'm writing 0 less than phi less than pi by 2. And to find that phase difference, the relation tan phi is XL by R, L omega by R. And power factor cos phi, power factor, it is R by Z, R by Z, Z is root R square plus L omega square. If you substitute that, root R square plus L omega square here, cos phi power factor you will get. And the average power in this LR circuit, to find the average power, you need to use ERMS, RMS EMF, into IRMS into cos phi, power factor R by Z. Then CR circuit. CR circuit impedance formula, that is root R square plus IC capacitive reactance square 1 by C omega square R square plus this. And same phase difference 0 less than phi less than pi by 2. Phase difference lies between 0 and pi by 2. And tan phi, to find the phase difference, tan phi capacitive reactance by resistance 1 by C omega R. Using this, you can find the phase difference. And power factor, again cos phi value R by impedance. In this, impedance is this root R square plus 1 by C omega square. Then power also same, ERMS, IRMS into R by Z. And the last, LCR circuit. In this LCR circuit, in this, impedance is root R square plus inductive reactance minus capacitive reactance whole square. This is impedance. And the phase difference, if the circuit is in LCR circuit is in resonance, that is inductive reactance and capacitive reactance, if they are equal, then this LCR circuit is in resonance. In that case, there is no phase difference between current and EMF. That resonance condition, let us see later. Phase difference not there, power is maximum, current maximum, power maximum. I am writing when the circuit is not in resonance. When the circuit not in resonance, then the phase difference between current and EMF of the source tan phi is xi L minus xi R by R. When the circuit is in resonance, this inductive reactance minus capacitive reactance, sorry, this is IC, inductive reactance minus capacitive reactance will be equal to resistance R only. In the resonance condition, equal to R, then you will get different relation there. Not equal to R, later we see that. And this power factor, again you have to write cos phi value R by Z. So these relations, impedance, phase difference, power, power factor for all these circuits, once you have to practice, not once, repeatedly you have to practice these relations. And this circuit, LCR circuit, when it is in resonance, in CR circuit, current leads by pi by 2. In LR circuit, by less than pi by 2. In LR circuit, current lags by a phase angle less than pi by 2. Now in LCR series circuit, which is in resonance, when it is in resonance, when the inductive reactance, capacitive reactance are equal, when L omega is 1 by C omega, that means when omega is 1 by root LC, this is called resonance angular frequency. Resonant angular frequency of the source for LCR circuit is this, and the frequency, resonant frequency 1 by 2 pi into root LC. Now, suppose if the angular frequency of the source is less than the resonant frequency required. Resonant frequency depends on L and C. The values of L and C. What is L? L. What is L? What is C? What is psi L? What is xi C? Students will have some confusion. Xi L is inductive reactance. This is inductive reactance. This this is also capacitive reactance. This is C is capacity. Capacity or capacitance. L is coefficient of self-induction of that inductor, also called as inductance. L inductance, psi L is reactance. Some students will have confusion in this terminology also. So L is the inductance, C is the capacitance of the capacitor used in the circuit. Now, the resonant frequency depends on the values of L and C. Suppose if the angular frequency of the source used there is less than the required resonant frequency. If omega less than omega naught, what will happen, you know? Xi L is L omega. Capacitive reactance is 1 by C omega. If omega is less, capacitive reactance will be more than inductive reactance. Psi C will be greater than psi L. If omega greater, omega less, psi C will be greater than psi L. Then this circuit will act as, LCR circuit will act as CR circuit. It will act as CR circuit. Means current leads EMF by some phase angle less than pi by 2. Similarly, if omega, the angular frequency of the source of AC, is greater than the resonance frequency, then what will happen is, when omega greater, inductive reactance will be greater than capacitive reactance. Then this circuit will act as a LR circuit. And current lags by some phase angle less than pi by 2. These are resonant conditions for LCR circuit. Now in this LCR circuit, one second, you observe that. Now I will clean this. In this LCR circuit, half power angular frequency conditions are there. That means half power angular frequency conditions means the current is maximum. The current is maximum in the circuit at one particular frequency called angular frequency called as resonance frequency. Their current maximum. In that case, at resonance, this circuit will act as pure resistor circuit, current maximum, power maximum in this. When the frequency is less than resonant frequency, this circuit will act as CR circuit. When the angular frequency more than resonant frequency, the circuit will act as LR circuit. Now, less than omega naught and more than omega naught, if you take two particular angular frequencies, there the power will be half and the current will be root 2 times less. Current 2 times, root 2 times less, power will become half. Those angular frequencies I am writing as omega 1 and omega 2. The difference of these two angular frequencies, omega 1, omega 2, the difference of these two is called bandwidth of this LCR circuit, angular bandwidth of LCR circuit. At half power angular frequencies, the relation is xi L, xi C, difference will be equal to R. Xi L, xi C, difference will be equal to R. Impedance, what is impedance in LCR circuit? Root R square plus xi L minus xi C whole square. Na? This xi L, xi C difference is equal to R square plus R square. 2R square, you will get Z equal to root 2R. At half power angular frequencies, inductive reactance, capacitive reactance, difference will be equal to R and the net impedance is root 2R. This in those derivations we did angular frequency. In that you will get these equations. Just I am reminding you. And the difference of these two is called as bandwidth, and that angular bandwidth of this circuit delta omega R by L. Angular bandwidth delta omega R by L. Frequency, if you write it, frequency, in terms of frequency, omega 2 pi f na. Delta omega is 2 pi into delta f. It is R by L. Delta f is R by 2 pi L. And there is one more in this, quality factor. What is quality factor? Resonant angular frequency divided by angular bandwidth, omega naught into divided by R by L. This R by L. L goes up. L omega naught by R. L by R into omega naught is 1 by 2 pi into root LC, no? Sorry. 1 by root LC, no? Omega naught. Then what you will get? One root L cancel here. 1 by R into root of L by C you will get. Quality factor of LCR circuit. If quality factor is more, the resonance is more sharp, the circuit is more selective. This you have learned, this is used in radio tuning circuits to match the frequencies. L should be more, R should be less to have more quality, more sharp resonance. If you want, L should be more, R should be less. So these points, whatever I have discussed now briefly, these points frequently you have to revise in this chapter. Come on, let us solve some problems now. Let us solve some problems. First problem. Look at that for the LCR series circuit shown in figure. LCR series circuit shown in figure. The current is observed to lead the applied voltage. Current leading. Current leading. Observe that. Current leading. It is LCR circuit. Current leading means this circuit is acting as CR circuit. Current leading means capacitive reactance is greater than inductive reactance. This what I understood is this from first sentence. Immediately after reading first sentence, I will get this idea. Now, an additional capacitor C dash, when joined with the capacitor C, with this capacitor which is already there, another capacitor is joined. Series, it is connected or in parallel, we don't know. Just joined he gave. Then the power factor of the circuit becomes 1 is giving, power factor becoming 1. Power factor becoming 1 means it is acting like pure resistor circuit. Means after connecting that capacitor C dash to C, Xi C becoming equal to Xi L. That's what is giving. Then only it will act as pure resistor and power factor becomes 1. What is the value of C dash? It should be connected in series or parallel. That all is asking. Xi C greater than Xi L implies 1 by C omega greater than L omega. But I want to make 1 by C omega equal to L omega. Next case, I want to make it equal by changing capacity. What to do? When 1 by C omega is greater, I have to decrease 1 by C omega. I have to decrease 1 by C omega value so that it becomes equal to L omega. That means I have to increase capacity. How to increase capacity? By connecting another capacity. How to increase? Whether we should connect that in series or parallel? Parallel. If you connect two capacitors in parallel, then the effective capacity becomes C1 plus C2. Na? So another capacitor C dash is connected here in parallel. Then the net capacity becomes C plus C dash. Then the capacitive reactance becomes 1 by C plus C dash into omega. This value is becoming equal to L omega. From this, I have to find C dash. First thing, that capacitor must be connected in parallel. Parallel. Second option or fourth option, one of them is answer. Now C dash you have to find. C dash. Find it. Cross multiply this. Easy. C, C plus C dash. C plus C dash is 1 by L omega square. Then C dash is 1 by L omega square minus C. That means C dash equal to, taking LCM, 1 minus C L omega square whole divided by L omega square. Third option. Finish. Next. I'm moving into next problem. The magnetic energy in an inductor changes from maximum value to minimum value in 5 milliseconds when connected to AC source, the frequency of the source. In these AC circuits, so suppose current increasing from 0 to I naught, maximum value, and then decreases from I naught to 0. This is half cycle, half cycle. Then again increases 0 to I naught, again decreases to 0. This is next half cycle. Positive half cycle, negative half cycle, you know. Na? So this is one full cycle. The time taken for this full cycle is called time period of that AC source. Then 1, 2, 3, 4. 4 intervals are there. Each interval is T by 4, T by 4, T by 4, T by 4. Like this, no? Now, if you connect an induction coil to AC power supply, what is happening? The current increasing, decreasing, 0 to I naught to 0, 0 to I naught, like that, it is changing. And that current, suppose, represented as instantaneous current is represented as, suppose, I naught sin omega t. Then what is the energy stored in inductor formula? Half Li square, no? Instantaneous energy I'm writing now. Half L, I is this value. No? If I substitute that here, I naught square sin square omega t I will get. Okay, this expression for energy, instantaneous energy expression is this. Now, when current changing 0 to I naught to 0, 0 to I naught to 0, then this energy also changes in a similar way. Now, energy changes from maximum value to minimum value, maximum to minimum, or minimum to maximum. How much time it takes? T by 4. Current T by 4, energy also T by 4. So that 5 millisecond T by 4. T by 4. But what is T? Reciprocal of frequency, right now T 1 by F. Is asking frequency there. Now find frequency from this. F equal to 1000 by 5 into 4, 20, 50 hertz you'll get. Okay, moving into next. In an AC circuit, inductor, capacitor, resistor are connected in series. LCR, impedance of this. A easy formula based. Z is root R square xi L minus xi C whole square. Xi LR, xi CR, R minus R, 0. This is equal to R. Z equal to R. LCR series circuit, which is in resonance, is giving. Next. In an LCR series circuit, an alternating EMF and current are given by the equations. EMF 160 sin 100t. current, instantaneous current, 250 sine 100t plus pi by 3. See, the units also important. Here volt given. Here milliampere given. Milliampere. Find the average power in the circuit. What is average power? Average power E RMS into I RMS into cos phi. Power factor cos phi. What is E RMS? E naught by root 2. I RMS I naught by root 2. E naught by root 2. I naught by root 2. Then E naught I naught by root 2 into 2. Root 2. This you'll get no average power. Now, what is this 160 E naught? This, what is this 250 into 10 power minus 3 I naught? Substitute there. 160 into 250 into 10 power minus 3 by 2 cos phi. Phase difference between EMF current pi by 3 is there, pi by 3 cos pi by 3 cos 60. What is cos 60? 1 by 2. Substitute 1 by 2 and simplify. You'll get power. Third or fourth, because answer starts with 1. Find it, find it. And one more, if you look at these equations, you must be able to identify that is which circuit also. Sometimes they'll use such questions. They'll give the two equations. They ask this circuit is LR, CR, pure inductor, pure capacitor, like that. So you must be able to identify. If you observe here in a current expression, EMF expression, sin omega t form is there. Current expression, you see current expression here. 100t plus pi by 3 plus pi by 3 plus is there here plus. That means current leading. Current leading here. And by how much phase angle? It is not pi by 2. If it is pi by 2, it is pure capacitor circuit. Current leading by pi by 2 phase angle, pure capacitor. This is less than pi by 2, 60 degrees is there here. Means it is CR circuit. Not pure capacitor. CR circuit this is. Next, I'm moving to next problem. This phase differences, one more. Suppose we have LCR circuit, something like this. In this circuit, phase difference between current and EMF of source, E of source, that is different. Phase difference between VR and I different. Phase difference between VL and VC different. Phase difference between VL and VC pi in these AC circuits. Phase difference between VL and VC is pi. VL, VC. Phase difference between them is pi. VR and I 0. VR and I 0 phase difference. Between current and EMF of the source EMF. VR is voltage of resistor. Between VR and I phase difference 0. Between current and EMF of the source. What is EMF of the source? Root VR square plus VL minus VC whole square. This is relation between VR, VL, VC and E. This E is the source EMF. Phase difference between current and source EMF. To find that, you have that formula. Tan phi equal to Capacitive capacitive reactance difference by R. That is between I and E. In this phasor diagram, current represented along x-axis, VR represented along x-axis, VL along positive y-axis, VC along negative y-axis. Net EMF is this. VLVC net is VL minus VC. VL minus VC, VR net value is E. Between VR and I, phase difference 0. Between VL and VR, 90. VR and VC, 90. I and VL, 90. I and VC, 90. This phi is phase difference between I and E, source EMF. You have now that phasor diagram. VL greater than VC, if you assume these two resultant is VL minus VC. VL minus VC. This is net EM voltage, means root VR square plus VL minus VC whole square, that is this. This is source EMF. Between that and current, phase difference phi. That phase difference formula is tan phi is xi L minus xi C by R. See, in a AC voltage source V equal to V naught sin omega t connected across a resistance capacitor which are in series. Series circuit, it is CR series circuit, and is giving condition R is 1 by C omega. R is equal to capacitive reactance is giving it. And the peak current is I naught, maximum current is I naught. If the angular frequency of the voltage source is changed to omega by root 3, then the new peak current is. Let us see this. In this circuit, R is equal to capacitive reactance initial condition. When angular frequency is omega, this is condition. Now, what is impedance? Root R square plus xi C square. But this is also equal to R only, no? So, this will be root R square plus R square. That means root 2R. Then the peak value of current I naught, maximum current I naught, maximum voltage V naught given here by Z impedance V naught by root 2R. First case. Second case, when the angular frequency of the source is changed to omega by root 3. This omega is not omega now. It is omega by root 3. Then he is asking. So in second case, what is the new impedance you find? New impedance. What is capacitive reactance now? 1 by C omega value, 1 by C omega by root 3. That is root 3 by C omega. Root 3 by C omega. What is 1 by C omega? 1 by C omega is R. 1 by C omega R. Na. So this is root 3R. Then what is the new impedance? Root R square plus root 3R whole square. The new capacitive reactance is root 3R, no? Root 3R square. 3R square you will get. 3R square plus R square. 4R square you will get. That is 2R you'll get. New impedance. So what is the new value of current? I naught dash V naught by this new impedance. Z dash I'm writing. V naught by 2R. But according to this first equation, what is V naught by R? Root 2 multiply like this. V naught by R is how much? Root 2 into I naught. So V naught by R is root 2 into I naught by 2. One root 2 cancel in this. You will get I naught by root 2. Finish. Moving into next problem. Calculate the capacitor reactance of a capacitor in order to run a bulb rated at 10 watt 60 volt. Bulb. Okay, bulb. I, in this chapter, one more, you need to practice transformer also. Transformer. Step up transformer, step down transformer. You know now, you have to practice this. In this transformer, you have one primary coil, then one secondary coil, all this. No? The EMF of primary coil divided by EMF of secondary coil must be equal to number of turns of primary by number of turns of secondary. Transformer ratio, this is. If number of primary coil turns more than number of secondary, EP will be greater than ES. Or reverse I am writing. If NS less than NP, then ES will be less than EP. Secondary coil voltage will be less than primary. That is step down transformer. Reverse condition. If NS greater than NP, ES greater than EP. That is step up transformer. This transformer ratio, efficiency of, and another in this, current in primary by current in secondary is inverse proportion. NS by NP. And next to that efficiency of transformer, you know, output power by input power into 100, that efficiency. This you need to practice transformer. Transformer works basing on mutual induction property. A bulb is used to operate, a transformer is used to operate a bulb. Like that, if it is given where that bulb is connected in the secondary coil circuit, bulb connected. Current in the bulb is 5 ampere, means that 5 ampere is current in secondary coil. So come to this problem. Calculate the capacitor reactance of a capacitor in order to run a bulb. There is a bulb, this bulb is there, this bulb ratings are given. Power rating 10 watt, voltage rating 60 volt. This filament gets damaged if the voltage applied to this bulb is more than 60. And if you apply 60 volt, the power dissipated in that filament is 10 watt. That's what is giving. Rating means that. But you are connecting this to a source of 100 volt. AC source of 100 volt. Array, more than 60 you are connecting. Then it gets damaged, you know. So somebody else must be there in series. What is that? You are connecting capacitor, you are connecting. One capacitor. What should be the value of that capacity to run this safely without getting damaged? Is asking that. That is the question. Means the source voltage is 100 now, RMS. If they don't mention anything, peak value, maximum value, amplitude of voltage, like this, if they don't mention anything, just voltage, if they give it is RMS value. RMS voltage of this source is 100. and this bulb filament should have 60. How much voltage this capacitor should have? First you tell me. They are not asking here, just I am asking. Just asking. What is this capacitor voltage? Here, E must be equal to root VR square plus VC square. In AC circuits, you need to use this now for voltages, not E equal to VR plus VC. E is root VR square plus VC square. This you have to use. E square is VR square plus VC square. E square is 100 square. VR square is 60 square plus VC square. VC square is 100 square minus 60 square. That is 80 square. VC is 80 volt. This capacitor's voltage will be 80 if you connect like this. Okay, this is not asking this. He is asking what is the capacity. Just I have explained that also for you. Now, what is the capacity of this to have this to operate this bulb? Is asking. What is the power dissipated in the bulb? 10 watt. 10 watt. That is the power in the circuit also, because capacitor power in capacitor 0. No? So this is 10 watt. What is power formula? Power formula ERMS IRMS into cos phi power factor R by Z. This how I am writing is ERMS. IRMS is again ERMS by Z impedance of the circuit. Source voltage is ERMS by net impedance of the circuit Z into R by Z. Then this power how much given? 10 watt. 10 given. ERMS 100 given. 100 into 100. 100 into 100 by Z into Z. Z square into R. What is R? R is the resistance of this bulb filament. Resistance. How to find resistance? For bulb, he gave voltage rating, power rating. Power is equal to, bulb power equal to, means this filament is a resistor now. That resistor, power in this resistor is equal to, that resistor voltage VR square by R. V square by R. VR, I am writing. What is this VR? 60. This filament voltage is 60. This power 10. I'll find R, 60 square. This implies this is R equal to VR square by P. No? VR square means 60 square. No? 3600 by power 10. No? So resistance of the bulb filament is 360 ohm. So this R is 360. From this you find Z square. Z square 10 cancel now here. Z square you find 36 into 100 into 100 Z square. What is C now? He is asking. From this, find that. He is asking the capacitive reactance by C. What is Z square? Z is root R square plus IC square. No? Z square is root cancel. R square plus IC square is equal to 36 into 100 into 100. Is asking IC square. Where I have to write? Where I have to write? Here I'll write here only. Sin C square equal to 36 into 100 into 100 minus R square. What is R? Filament resistance 360. 360 square. 360 square is 36 square. First I am writing. 36 into 36. into another 10 is there, no? Square. 360, I am writing 36 into 10. For this square, I am writing 36 square, 36 into 36, 10 square, 100. Now 36 into 100, 36 into 100 common now there. 36 into 100, 36 into 100 common. If I take them common, what I will get finally? Xi c square equal to 36 into 100 common in these two. Here 100 minus 136. 100 minus 36 is 64. So xi c square is 36 into 100 into 64 you are getting. Xi c root of this. 6 into 8 into 100. 6 into 8 into 100, root of this 480. This is if they ask you what is the voltage of the capacitor, just I have explained. In this problem, he has not asked this. He has asked capacitor reactance. E naught sin omega t, in what time will the EMF reach half of its maximum value? E equal to E naught sin omega t, instantaneous EMF. At what time E will become E naught by 2 is asking. Ding ding, cancel. Sin omega t is 1 by 2. Means this omega t must be 30 degrees. 30 degrees means pi by 6. 2 pi by capital T into small t is pi by 6. Pi by cancel. Small t equal to capital T by 12 you'll get. Okay, students, all the best. May the Almighty bless you all.